Okay. Let's begin. Today we're still going to be using limits a little bit, so hopefully you guys understand those. Except we're going to be using it to talk about another topic, a very important topic. It's called continuity of functions. So I'll give you one of the mathematical definitions for this, and then we'll talk a little bit more about intuition, and then go into some examples. So here's a definition. A function f of x is said to be continuous at a point where x equals a if the following equation holds. So this was, of course, one of the bonus on the quiz today. Does anyone know the equation that would need to be continuous at a point A, where x equals A? Well, the answer to that was this equation. The limit as x approaches A of the function should be equal to f of A. That equation defines what we call to be continuous at a point. This is continuous at a point where x equals a. We also have a notion of being continuous in general, or having some sort of general continuity, and that is the following. F is said to be continuous. Right? So not continuous at a point, just continuous, period. If it is continuous at all points in its domain. Okay. So basically, if this equation is going to be true for every single point A that is in the domain of the function, we say that function is continuous in general. However, you can talk about continuity at a specific point, and all you have to do to check continuity at that specific point is to check if this equation holds. If this equation will hold at every single point in the domain of the function, then the function is said to be a continuous function. So here's what that equation breaks down to. It's a very simple and short equation, but it has a lot of meaning behind it. I don't know, should I say intuitively? F is continuous if it has no holes, gaps, breaks, jumps. Basically anything that won't allow you to, in theory, if you can graph the function by hand, you can do so without lifting your pencil off the page. That's the idea. Now that seems like a very, that you can sort of see, like, to be continuous means it's always continuing. You can just keep drawing the function, and you don't have to break anything or jump over a hole or do anything like that. Very intuitive. It might be surprising to you that that notion or that idea can be summarized by a single equation that's this short. But let me illustrate to you that this equation actually holds everything you would need to hold in order for this possibility to happen. So let's look at situations where this equation breaks. Here's one example. say we have something, but there's a hole. We've seen functions like this already. Now, intuitively, to us, that will seem like something that is not continuous, because there's a hole. I'm drawing this, I have to lift up my pencil to jump over this bad point and then continue, right? There's a hole in this function. It's not continuing. You could also have a situation where you're doing like this. And you jump up here. Right, so we can be here at the point A, or here at the point A. Let's look at some other situations that to us it would clearly be the case that it's not continuous. Intuitively we know we can't draw that without lifting up our pencil and having to jump over something. Well, there's the slightly opposite case would be true, but in principle it's going to be the same as that situation. You can also have a situation like, let that be the A, your function is doing something like this. You can also have a situation like this. So function is continuing. Oh, there's a hole here, but we jump up here to fill in the point, and then we start to jump back down here and continue. So that's another situation, right? You can sort of imagine pretty much every situation that you can think of. These are just a few illustrations here, where there's going to be a break or a jump or a gap in your graph, something that's some sort of chasm that you have to jump over. And now you can start to examine the elements in that equation. In this one, does the limit exist as you approach A?
Yes.
Yes. Right? Remember, we don't care about the hole, we don't care about being at the point. However, if we get close to that point, we seem to converge to a point that does have some y value, which we can call L. So this is L. However, what is f of A? It's undefined. So obviously, this is not equal to that because this will give us a number, but that doesn't give us anything. This equation does not work, the one that I wrote before, and you can see what this kind of situation does is it creates a hole. What about this? Does the limit exist here? Here you will realize that the limit as x approaches A of f of x does not exist. Does the function exist? It does, right? Whatever this value is, let's call that. So again, the equation that I wrote down is not going to hold because the limit messed up. The limit doesn't exist. The left side of the equation doesn't hold. Even though the right side gives you some meaning, the left side doesn't. They're not the same. This kind of situation will result into some sort of jump. You'll realize that this is also very familiar. Limit does not exist. Here your f of A does exist. It can be some value c, but they do not coincide. Therefore, it results in a jump. Here, there's some context in which this would be said to not exist, but for us, we consider this infinity. It's not even a number, right? But on top of that, our f of A is undefined. Right? So pretty much any situation where these guys don't match up, right? This one could give you infinity. You can't actually define a function to be at infinity, so that will never work out even if the limit is infinite. If you look here, notice that both of them actually work out, right? The limit does exist. It's equal to some value L. L would be here. The function f of A is also defined. Let's say that's at B. However, you'll notice that L is not equal to B. This will actually result in a situation that looks like this, where the graph is fine except for one point is misplaced. And there are many more countless examples that you can think of. But I assure you, whatever thing you can think of that's going to break the intuitive notion of continuity is also going to break that equation that I gave you. That equation will cover all situations in which these breaks may or may not happen. As contrasted with, if you look at this, what would it look like if you could continually just draw something, right? Here's a point A, but you don't really have to worry about it. You're going to just draw the function passing through that point, right? And let's say f of A is some value equals to B, but it turns out the limit as you approach that will also give you the exact same y value. So you will end up in a situation where your limit as x approaches A of f of x exists, f of A equals B is defined, and L equals B. Now when you look at that, all these three things coming together creates a situation where you can literally pass through a point without having to jump out of the way. Right? Once this equation holds, it is continuous, right? Whether or not you know what the picture looks like, you would know how the picture would have to behave moving through that point. It's not going to be a jump or a gap or a hole or a break or anything crazy that you have to deal with. The function will just continue to happen. So that is defining what a continuous function is. And this is, again, another example in which in math we want to take a very intuitive idea and make it concrete somehow where we can actually put a number on it, and this would be it. The idea of being able to continually draw something without lifting your pencil off the page is captured by that single mathematical equation. Now, let's unpack the definition a little bit. I want you to be aware that three things need to occur to be continuous at a point. So one, the function must be defined at the point. Which means when you plug that input into your function, there should be an output, it should be meaningful, it should be a real number. Two, the limit as you approach the point of the function must exist. And again, some things worthy of note here for the limit to exist. One, we want it to be finite, because if it's infinity, positive or negative, it's definitely not going to coincide with 1. And you must understand that the one-sided limits must agree. So you might be in a situation where you have to actually consider the function from both sides as you approach A. You should just be aware that this might be something that you should have to consider, and you should be worrying about it. And so that is the limit as x approaches A from the right side of f must be equal to the limit as x approaches A from the left side of f. Right? So that has to happen for part 2 to work, but those two things must work. However, you should notice it's not good enough for those two things will work. Here's a situation where they both actually work out. But thirdly, the above two must be equal. So you have to make sure that three things are in place in order for continuity at a point to happen. You must have an output value at that point, the limit must exist at that point, and the values that both of these guys give you must be the same. Whenever that happens, there's no break, there's no gap, there's no hole, there's no jump. Your function is just very nice. You need something else to be nice in the calculus sense, but that's very nice in a more general sense. Continuous functions are very nice to work with. Functions that are not continuous, that have breaks, it's hard to do math with these functions in general. And more importantly for us, in the gaps, in the holes, we actually can't do calculus, which is why we even care about this thing. Calculus is only going to work for us where the function is continuous. So if at this point I asked you to find the derivative, then it's not going to exist. Right? That's going to be a problem for us. Don't worry if you don't know what the derivative is, we'll get to it soon. But But it's important to know calculus is not going to work where the function is misbehaving. So we need to know what it means for a function to behave, and then maybe we have a shot at calculus working at that point. So we're going to spend the next couple of lectures talking about continuity and some of its consequences, and also we're going to do some examples so that you can get a real handle on it. So let's actually do that now. I'm going to write some examples on the board. We're going to determine where they're continuous. Yes.
So even if a function is not defined at a specific point, but we're discussing about a domain that's outside that point, and it's like continuous in that domain, will that be continuous?
Give me an example.
So just make like a point that's continuous,
Yeah.
and like make a circle, just like that.
Mm-hmm.
But we're talking about a domain that's like outside the circle.
So like we're living over here.
Yeah. So it will be continuous.
Yeah, oh, in this section it would be continuous, right? So that's what I'm trying to talk about here, so to determine where it's continuous. In this example I gave you, let's say this happened at 2, but everywhere else seems fine. I would say it's continuous on the interval minus infinity to 2 and 2 to infinity, but it's not including 2, right? So when I say where it's continuous, that's what I mean. So it's possible for it to be continuous in some parts and not other parts, right? But if you ask specifically the question, is it continuous at the point where x equals 2, the answer is no. But it could be continuous elsewhere, right? And there are functions in which, along their domain, they're literally continuous everywhere, and those things you just say they're continuous in general. And you can just say, this is a continuous function, and the assumption is, no matter where I am, this kind of thing is happening. There's no hole or jump. But there are some things that will break in some sections, but they're okay in other sections. But it's also important for you to identify what those sections are where you might have a problem. Right? And you can identify that by using the equation. Okay, so determine where the following are continuous. I'm going to write down a bunch of functions, and we're going to talk about where continuity is happening. Piecewise function. So we're going to work on A through D together, and then I'll have you guys try your luck at E, and hopefully by then you can sort of see how things will fit together. So look at A, f of x equals x squared. So that's just a parabola. Passing through the origin. Where do you think it's continuous? What would you think? What would you say? Yeah?
Negative infinity to positive.
negative infinity to positive infinity. It would be continuous at all real numbers. Let's see why. Well, let's look at f of a. F of a is just going to be a squared because the domain of f is everything. So for any a, for any real number a, I can plug it in and the result will be a squared. So that is defined and it's going to be a real number. Whatever I plug in, the square of that number is going to be the output. Now let's look at what would the limit of approaching a random point of x squared looks like. So remember, the limit is just caring about the y values as you approach the point A. You don't necessarily care about being A. However, it's possible to be at A. You can't get closer to that point than actually being there. And so you'll realize that the y values are converging again to a squared. Right? This will be a limit where we can use step 1 of our strategy to solve that. It will actually give us a squared. You'll of course notice right after that, limit as x approaches a of f of x is equal to f of a. So, and this is working for any real number a. So f is continuous on minus infinity to infinity, the entire real line. A way to say this is f is continuous everywhere. So they'll literally use the word everywhere if it works on the entire number line. Which means no matter which point you are, you can be graphing x squared and you'll, in theory, never have to lift your pencil. You will never have a hole or a gap or a break or a jump or some sort of messy thing happening with x squared. It's a very nice function. Literally at any point on the number line you can find a value and limits will work out nicely there. Everything will be cool. In fact, because of the domain feature, all polynomials will be continuous on the entire real line. So that's just a thing you can know. Whenever you're doing calculus with a polynomial, you kind of don't have to worry about where you are specifically on that polynomial. Everywhere is going to be fine. It's going to be working out. What about b? Yeah?
Negative infinity to 2, union to infinity, where 2 is not included.
Okay, why?
Because if you set the denominator equal to 0, x equals to 2, and the denominator can't be 0, so you don't include it.
Okay, so we have f of 2 is undefined. Right? So that automatically breaks continuity there. Right? So not continuous at 2. However, otherwise, which you should be worrying about that as well. So that means if your a value is not 2, otherwise, you can actually find the limit of this function by simply just plugging in the value, because then it'll make sense. We can do step 1 of our limit process. But that would actually equal to the function evaluated at a. So you'll realize that it's continuous for everything that's not 2. At 2 it breaks, but everywhere else it's fine. This means f is continuous on this interval, minus infinity to 2, union 2 to infinity. At 2 it's not continuous because step 1 of the 3 steps don't work. The function isn't defined, but pretty much everywhere else you can just plug in the number and it's just a fraction and it'll be fine. Well, not a fraction technically, it'll be some sort of algebraic expression. It'll be a real number. So that guy will work everywhere you are not 2. Let's look at part C. So now I create a piecewise function where x squared minus 4 over x minus 2 is only one of the parts. And I say I'm not going to plug in 2 into that expression, right? It's illegal anyway. So I'm going to say we're not using 2. In the event that you're at the point where x equals 2, I want you to define the output to be 1. Where is that continuous? Yeah?
It's not continuous. F of 2 will be defined and the limit will exist, but they won't be equal to each other, so something like this.
Okay. 2 is still a problem, in other words. Right? So here at 2, you'll realize that the limit as x approaches 2 of our function is going to be what? So the limit as x approaches 2 of x squared minus 4 over x minus 2, what is that value?
4.
It's going to be 4? How do you know?
It's x minus 2 x plus 3 over x minus 2.
So that's going to give us the value 4 as x approaches 2. What is f of 2?
1.
It is 1 by definition. Right? They told us when x is 2, the output is 1. 4 is not equal to 1, last time we checked. So this means f not continues at 2. Otherwise, we're fine by that same reason. So ultimately, f is continuous on the same thing. It's still not going to work at 2. You can also realize this from the picture. We've actually drawn this before in class. You might remember the graph looks like this, except when it's passing through 2, there's a hole. So obviously that won't be continuous, there's a hole there. In this one, we kind of tried to fix the situation. I don't know where we're going to throw this. In this one, we kind of tried to fix the situation. The graph of this looks very similar. The difference is, at 2, they filled in a point here. So while this is at level 4, they filled in a point that's at level 1. You will still need to pick up your pencil to fill in that point and then continue, right? It still breaks the continuity definition, right? There's still a gap there, right? So here there was just a gap and no one was trying to do anything about it. Here someone tried to do something about it, but they totally missed the target, right? So it still has a break there. Let's look at D. Here f of x is defined as x squared minus 4 over x minus 2. If your x is not equal to 2, we define it to be 4 if your x is equal to 2. Where is that continuous? Yeah?
Everywhere.
That is continuous everywhere. We've kind of done a lot of the groundwork. You'll notice here that f of 2 is defined, it's actually equal to 4. You'll also notice that the limit as x approaches 2 of f of x is equal to 4. We showed that here. This means f is continuous at 2. It's also worth mentioning that otherwise we're fine. So ultimately, we're definitely okay if we're not at 2, and at 2 it actually worked out this time. So it turns out that all numbers are okay. F is continuous on the entire real line, it's continuous everywhere. And this situation is the following. Again, it starts out in the way we know it would. There's a hole there. The hole is right over a point where the x-coordinate would be 4. And then someone went and, you know what, there's a gap here. Let's actually fill that in at level 4. So there was a hole there, but we filled it. Now, in theory, this function can be drawn without lifting our pencil off the page. This is now a continuous function. And now, this particular function behaves exactly like the function y equals x plus 2 in every way. It's not discernible. And x plus 2 is a polynomial. That's a very nice function to do math with. Right? So I went from a very ugly function with a problem, and I can fix the situation to get a very nice function that kind of works out everywhere. So, and again, the idea is working on a function where it's continuous is going to be important. You need to be able to identify it, and there are some times you can even fix the problem, like we could here. So work on the last one. Where is that continuous? Give you guys a couple minutes to decide that. Okay, what's the answer? Maybe someone who hasn't said anything yet today. Amanda?
Fx is continuous at all points.
Okay, justify.
Because you can factor out x squared plus 5x plus 6 to x plus 3 times x plus 2, and you could cancel out that.
Okay. Why would you want to do that? What are you doing?
To see where, because you know there's a hole there, but to see where x would be. Oh, is it supposed to be x is not equal to? Or something?
-2.
Okay. To see where the limit would be if there wasn't a hole there, because you can already tell there's a hole there just because the denominator would equal 0.
Okay. But what specifically are you working on now? This whole factoring thing, what are you trying to find?
I'm trying to see like where the limit would be, so if the hole was...
The limit, you're trying to find
Yeah,
a limit.
I'm
So
trying
that's,
to find
that's what I want to make sure you say. I want you again to have it of, again, going through the principles in a certain order, knowing what you're looking for at any given time. One of the 3 things in that list was the limit. So what you're working on at this point is the limit. So yeah, so the first thing you decide, you realize that x equals -2 is probably going to be an issue, so you find the limit as you approach -2. And so now you realize, okay, yes, we can factor this. This happens to be, what is it, x plus 2 times?
X plus 3.
So that would cancel, and what would you get here?
1.
You get 1. The next thing you'd want to check is the value of the function at that point. Is the function defined at that point?
Yes.
Is f of -2 defined? Yes, and what is it?
1.
It is 1, again by the definition here. It's given definition. So what does that tell you?
F of x is continuous at all points.
No, what I wrote down? No?
Or f of x is the limit of x approaches -2 equals -2. Or f
Yes,
equals
but
2.
what does that mean?
F is continuous at -2.
At -2. Okay. To be able to say it's continuous everywhere, that's a separate consideration. All you looked at here was the point -2. Now you have to say, you have to just make a statement so I know you're actually considering it. You know, otherwise we're fine. Or you can say, if you want to flesh things out, or you can say otherwise the limit as x approaches a of the function of say x squared plus 5x plus 6 over x plus 2 is just going to be you plugging this thing in, and that's just the value of the function at the point. And then you can conclude f is continuous everywhere. So checking this equation, you can actually only do it for one point at a time. X equals -2 was obviously a point of concern because we had a piecewise function breaking up around that. So you probably should check that and then worry about the other things, right? And worry about the domain of the function. So sometimes, even if I said define this at 3 and 3 here, -2 would still be a problem that you'd have to check. So you have to be very familiar with domains of functions and all that. So -2 would be an issue here regardless. But you can deal with that specific point. Then you have to worry about the other points. The other points are fine, so everyone works out, and it's continuous everywhere. What else do we do? Okay, do the same, answer the same question for this. F of x equals sine x over x. Where is that continuous? Some question, actually same question. Yeah?
Everywhere except 0.
Everywhere except 0. Can you write out a justification?
Yeah.
Okay, go. What is the first thing you check?
I would check whether the function is defined at 0.
Right, f of 0 is?
Undefined.
It's undefined, right? You divide by 0 there. And so that automatically says f not continuous at 0. You don't even have to check anything else. Are there any other issues? So at 0 there's a problem. Is there a problem anywhere else?
I feel like you want me to say yes.
No, don't worry about what I want you to say. I want to say the right thing. Sine x over x. Can you think of anywhere other than 0 that would be an issue? Any number that you can plug in that's going to be like, nope, not going to work. Is there any other number?
Maybe 2 pi, because that 360.
Okay, what is sine of 2 pi?
Yeah.
It's 0. So I'd have 0 divided by 2 pi. Is that a real number? That's fine, that's
Yeah,
0. That works. Where is sine actually defined? Does the sine function have a gap? No, it literally does this forever in either direction. There is no gap, right? Same, what about the function x? Does that have a gap? No, it literally does this forever. There is no gaps. Individually, they're fine. I can plug anything into either of them. The thing is now when I throw in a division, now I have to worry about denominator being 0, right? So it's not continuous at 0, but clearly 0 is the only place that an issue can happen because individually these functions work no matter what I plug in. 0 is only an issue here because a division is in play, right? Otherwise, they're okay. The numerator and denominator are continuous individually. We'll actually state this in like a theorem where we can say if you know individual functions are continuous, then their product is continuous, their sum is continuous. We'll actually state that, but just thinking through the ideas here, that should be become clear with a little work. Huh?
So if we flip the equation, it's x over sine of x.
Yeah.
The limit is still 1, but wouldn't it be like not good?
Yeah, but where it's continuous, there will now be an infinite number of points that will have trouble. Pretty much every integer multiple of pi would be a problem. So you literally have a bunch of, it won't work at 0, it won't work at pi, it also won't work at 2 pi, right? It also will work at 3 pi.
How do you write that one?
You can say something like continuous for all x not equal to n pi, where n is an integer. It's a nice way to write it in a sentence if you want. Okay, so this function is continuous everywhere except 0. So you can actually make that statement. F of x equals sine x over x is continuous on pretty much, as long as we're not 0, we're fine. Okay, here's a follow-up question. Can we fix this? So here's a function, it's misbehaving somewhere with division by 0. Can you think of any way to fix that situation? To make the function even nicer than it already is? Right, so here's a function. You probably don't have to know what the picture is. So we know the limit is 1 as you're approaching the origin. It looks something like this. So here's a function and there's an issue. It's not continuous everywhere, which is like the gold standard of what I want to happen. Is there a way to fix that situation? Yeah?
You can make it a piecewise function and just define it at that point for what the limit is at that point.
The answer is yes. Sometimes we have functions that are trouble, and the previous example should have hinted this to you. Sometimes functions are trouble, but they're only trouble at certain specific, a finite number of points. You can always fix this situation. You can always sort of create a new function that respects the old function in the spirit of what it's supposed to do, but at the same time, it's nicer to do mathematics with. So what you could do here is you can actually redefine f of x by the following. Just make it a piecewise function. Let it be whatever it wants to be at the point that's bad, except the point that's bad. But at that point, it turns out I can literally just fix it by shading something in. Problem solved. What did I just do? Well, on the picture, I shaded something in. Mathematically, I defined it to be a certain output at that value. So this is a function that behaves like this function at every other point, except at the point where it's discontinuous. This one is now continuous, right? So this is like that function, but better. And pretty much with anything you want to do, this function will behave like that one, except this one has a problem at 0, and this one doesn't. Right? So whenever this happens, i.e. that means I'm talking about we can fix things. By redefining f at a finite number of points. We say we had a removable discontinuity. So it wasn't continuous there. Another way of saying that is saying it's discontinuous there. However, if you're in a case where the discontinuity can be removed by just redefining some sort of piecewise, redefining your function as a piecewise function, this is called a removable discontinuity. There are discontinuities that we can't fix. These are called essential discontinuities. And they come in several varieties. You can have infinite ones, you can have jumps, you can have etc. But we'll talk about those next time. For now, we'll stop there, and we'll pick up with this on Friday. I will see you guys. Any questions on? So read this over, maybe practice a few problems. There was actually a bonus problem on the quiz about continuity. You can try to see if you can figure it out. And I'll see you guys on Friday.